Okay, so in this video, the focus is on the velocity as a vector quantity, but indeed it is a bit more than that. So if we go little bit deeper into detail, we will see that we now draw a connection between different fields of maths and physics. So there is a connection here between the vector analysis and calculating with vectors, analysis, and physical modeling, so to say. And because we haven't been so far in maths that we completely understand the connection between these two topics, to be honest, I think you haven't even done the first topic in analysis that we need here, the concept to understand this. So that's why this video is going to be a little bit longer, because I need to explain some basic concepts in maths. Still, this will help you in the future when you get there in maths to, if you have an example from physics, that certainly helps you to strengthen that concept in maths and understand there a little bit more. Normally it's better to do it the other way around, but in this case that's what we need to do here. So we look at the different formulas in the script, and we start with the velocity as a vector quantity. So far we might already know that velocity is a vector quantity in physics. However, there was no need to treat the velocity as a vector. That means this is still a bit new, and I will come to that in a few minutes. However, I think that because I've never been teaching in S3, but I think forces have been introduced as vectors. They should be, and that's because the forces, they have a magnitude that gives us the strength of the force and a direction. So we already know that it makes a difference. There is a difference in the strength between different strengths of forces. So if I push a chair, for example, with a greater force, it will accelerate more. It will have more energy. It will cause more damage if it hits the wall, whatever. But there's also a difference in the direction. So if two forces act on that chair and they are of an equal magnitude but opposite direction, the chair won't move because it's in a kind of equilibrium. But if these forces act in the same direction, the total force will be twice as big. So here we have already seen that in a good example for vector quantities in physics. Now, with the velocity, it is more or less the same. In the last 2 years, we have been working with velocity as a quantity, but the only issue where we had to consider it as a vector quantity was when we put the minus in front of the v, because the negative velocity meant that we have a change of direction. And this was because we have only considered movements in one dimension. So there was only moving forwards or backwards, moving upwards or downwards. So there was only one direction and the opposite direction. So it was still possible to use the negative sign to indicate the direction. But now we want to look in two-dimensional cases of movement, and that's where we need also a direction, because if we want to calculate the location of a moving object in a certain time frame, for example, it is essential to know in which direction this is going. And we will see that the movements that we look at might even change their direction each second. So if we throw a ball at a certain angle, it's not hard to imagine that it changes its direction in each instant, and the same applies to circular motion. So now we could use the vectors in two dimensions that we know from maths. However, this makes things not always easier. So what we can do is we can separately look at the magnitude of the velocity and the direction. Yeah, so we still calculate with scalar quantities, so just numbers, and the direction can be given by an angle, for example. So now we come back to that formula, and I give you an example now. Let me just check. Okay, so we have a point C where we have an object, and this is moving with the velocity v1, and we see that the arrow is pointing at a certain direction, and its length is representing the magnitude of the vector. So here we are talking about the speed. Okay, so if we use the word speed, normally it means that we only consider the magnitude, and the velocity includes the direction. Sometimes I use velocity and I just mean the speed, but if we say speed, it is very clear that the direction of the movement is not playing an important role. I give you an example. When we want to, for example, we look at the GPS that calculates a certain route from, I don't know, Mondorf to Luxembourg City or to Paris, and there we only need the speed, although the roads are pointing in different directions, so we should have a two-dimensional problem, and it's even going upwards because we have hills in between. But if we take the road, if we take the route along the roads, and then just imagine it was a string that we can, strengthen. What do we say? stretch, then we don't change the distance, so we can like unfold it and make it into a one-dimensional quantity or transfer it without any difference regarding the time that we need to our destination. But here again, we have this object where the cross is. We have a velocity which with the object is moving with, and now we have a second velocity. So this could be the wind, for example. Okay, so we are riding with a bike in the direction of the first vector and the magnitude, and we have the wind is coming from the side. It could also be a sailing boat. So what happens now is that the two quantities are have to add. So what happens with this object, and I'm sorry, I have made this video in German before, and now I just remembered that I wanted to have another example before. So if I'm going a step back for the addition of velocities, so if we have I'm explaining that later on here with a train. So if you read further, you will see that I'm explaining a situation on a train where velocities are added. So very briefly, the train is moving and I'm moving in. Well, I'm sitting on the train, or I'm moving with the train, and inside the train I am walking. So if I'm walking in the same direction as the train is moving, we would add the two velocities or the two vectors because they are pointing in the same direction. So we never had to use that specifically the rules of adding vectors. If I'm moving in the opposite direction, this could mean if I'm walking with the same speed as the train is moving forward, I'm moving backwards, that a spectator that is standing outside of the train will observe me staying at the same position all the time because the train is moving with the same speed but in the opposite direction. So we see here that we still add the two velocities, but one of them has a negative sign, so actually we subtract one speed from the other. But now we come back to this example here on GeoGebra with the two vectors pointing in different directions and not the opposite direction. So we still try to add these because we know how to add the vectors, and we see here that the result is the vector u, and we can shift that. That's what we know from maths. So we put the origin of the vector into that object that was indicated, and that's where we end up. So can move that. Okay, so this is the resulting velocity of the two separate velocities that we have of this object here. So once again, we are moving with v1 in a certain direction, but the wind is blowing in a different direction with a different speed. That also makes us move in that direction. So the resulting velocity is the sum of these two vectors, and this will be the vector v. This already explains the vector properties of this quantity. And so when we look at the formula, the vector v is the ratio of delta s divided by and delta t. So delta t, the time can never be a vector graphics because the time only knows one direction. Yeah, the time can move backwards. We'll see that maybe later or at university. But this is, but it can't move in any other direction. Time is just going into one direction normally. But the distance, and that's what we see here, is the quantity with the vector properties that also gives the vector properties to the velocity. Because in this equation we need to have if on one side we have a vector quantity, there must be a vector also on the other side. And this is definitely the delta s. So we now come to another case. This refers to that exact formula. So we have, when you look at the axis, we have on the x-axis we have the time, and the y-axis is the distance. So now we're looking at a linear movement. So if we want to calculate or determine the velocity of this movement, in this case it's the speed, we look at 2 points, and between these 2 points there is a certain time interval. In this case delta t is 2 seconds. And when you look at the second formula, that's what applies here also. So the delta t is t2 minus t1, that's 10 minus 8, and that is 2. And the delta s would be, it's a bit easier when we zoom in here a little bit. So here we have S2 is 5 minus S1 is 4, and that is 1. So according to our formula, V is delta S by delta T. We would have 1/2, so that's 0.5. And if you look at the left side, you see the equation that describes this straight line. That's F, the red one. It's 0.5 times x. So we see that indeed the slope of this line is equal to the velocity, and that's what we know from maths. The gradient is delta y by delta x, and here we have other quantities in physics, so we have delta s by delta t, and that is according to the definition, it's the velocity. But in maths, if we interpret this this ratio, that would be the slope. So now here we are talking about average speed. Why is that? Because in this case we can see that the slope is constant, so the speed is constant, so average speed is the same as the momentary speed for each time. But that's exactly the point where we get something, or where we learn something new, because we have already been looking at movements that changes their speed or their velocity. And here is an example. So the graph of G shows a parabola, and if we consider this as the time distance graph of a movement, then we can see that the graph is getting steeper, so the slope is getting higher. That means that we have an accelerated movement, obviously, because in the first second or time unit, we have a distance of 1. So that's what we see here. Yeah, and if we go a bit further, in the next second, we already have a distance of 4. So the difference between the first and the second would be 3. So in the first seconds, it was a distance of 1 unit. In the second, we have a distance of 3 units. And so the distance that we travel per time unit increases, and that means that we have a change in the velocity. Now we want to find out how can we determine the velocity in this case. And this is a bit tricky. We stay here. So we start with 2 points, so second 2 and second 3, and we bear in mind our formula from before, where we calculated the slope. Now, between the points F and G, so between 2 and 3 seconds, the slope is 5, and now that means that the average speed in this on this interval must be 5. But if we look at the graphs, we see that the slope of the graph itself is at point F. The slope is smaller than our straight line, and at point G, the slope of the graph, of the purple graph, is higher. And that means that at point F, the speed or the velocity must be below 5, and at point G, it's above 5. So that's when we get the when it makes sense to talk about average speed, because that is so. How can I explain that? If we have, we just look at the. Let's consider point F as the starting point and point G as the finish. And we have an object. The black one is just moving with a speed of 5, and the purple object is following the movement that is described by this parabola. And they start at point F at the same time, and they will also, but the purple one is starting with a slower speed and it ends with a higher speed, but they will meet again at the same point. This is point G at the same time, because the speed of the purple one has been changing and has been increasing. So at first it starts, it will be a bit behind the black object, but exactly at point G it will be at the same position and overtaking the purple object, the black one. So that's called the average speed, but the momentary speed doesn't make sense to have a time interval and talk about momentary speed of the purple one, because obviously it changes. So what we need to do is we decrease the distance between the 2 points. And what we see here is that if we are moving with point G towards point F, the distance between the two graphs, the black line that still indicates the average speed, and the purple line that describes our movement, they come closer to each other. So we continue with that, and we see that the black line and the purple graph are getting closer to each other. And still on the left side, you can see in the command line there is, it's called m equals Steigung of h. It's 4.2. So we started with a slope of 5, and now we are down to the slope of 4.21, meaning the speed, the average speed between the point F and G is now 4.21. And we see that the average speed is now decreasing because we are moving point G more and more towards point F. So the time interval between the 2 points that we measure is becoming smaller. And that means that the measurement of the velocity becomes more accurate. So now there's only a difference of 0.05 seconds between the 2 points. And this is how we measure the momentary speed also if we look at the car or a bike, because the speed is something, and you will see what happens if 2 points are exactly on top of each other. The black line disappears because it's defined as the connection line between 2 points. And if the 2 points are identical, there would be an infinite amount of straight lines going through that 1 point. So we don't know the direction. And that's a mathematical problem that we don't treat too much in detail here. But the important thing is, now we see that we can't even see any difference between the black straight line and the purple graph. So we look at the slope again, and it says it's 4.01. And if we go towards the point F even further, now it says here already it's the slope is 4. And now I explain that formula in the script where I say velocity v of the momentary speed is the limit of delta t going towards 0. What does it mean? If we look here at it, if we consider a triangle like the red one between F and G, we see that delta t, which is the baseline of that triangle, is getting smaller and smaller. Now delta t would already be 0.002. So we have seen what happens if we want to have the momentary speed at one point. We have seen what happens. And another reason why this is happening is a result of the formula, because you see that we are dividing by delta t. So if we set delta t to 0, a single point, that would be, we have a division by 0 which is not defined. So we can't really do that. And that's why we have to use a method called differential or differentiation. That's what we will do in maths, or you'll do with somebody else a bit later. But what we can see here already is we can move point G infinitely well, we can make delta t infinitely small, and that's what's meant by this expression limit. So we move delta t towards 0, but it can't get to 0. But what we see here is that no matter how far we go, how close we move point G to point F, the slope remains 4. And that means, well, if we go beyond that, we see now the average speed is getting smaller, so we are already at 3.99. So here it was above 4, there it's below 4. So we can already see, without proving that, that the momentary speed at point F must be 4. So that means that the slope, and now we call it gradient, at this point is 4. And now we zoom out and we can already see that this is in the case where G and F are at the same location. The black line would be a tangent line of this graph, indicating the gradient or the slope of the parabola at this point. So we are getting towards the end. Well, there is another, the equation has a third part here. So the limit, when we have the limit of delta t towards 0 of this fraction here, we can write this as ds by dt. And the d is basically the same as the delta, but it indicates that the numbers are infinitely small. Okay, you know what I mean? So in fact, we have a situation here where we divide 0 by 0. Okay, but as I said before, that's a mathematical problem that you will treat in maths later on, or maybe you've done that before already. But in physics, we want to use this. So we just need to understand what it means and not where it comes from. Exactly. So this just indicates that the delta t is 0. So we're talking about the momentary speed, and that's why we don't write delta t, because delta always means a difference. When we write dt and ds, we know already that this difference is actually 0. Okay, although we know with our current methods this wouldn't be possible, but we have seen on GeoGebra that there are ways of finding out the momentary speed, and well, that's about it. So if we wanted to find out now the acceleration of this movement, we would do exactly the same for each point of the graph. See here already is point F is not on the graph every time. So if we did this for all the points on the parabola and we indicate them in our coordinate system, we would get this line. So we have seen already that here we have a slope of 4, and you can see that, okay. But here, for example, we have the slope would be 2. I hope you believe me. So on the green graph here we have the value of 2. So if we did that for all the points on the parabola, we get this green graph, and that is then we can interpret this as the acceleration, because now that is the change of the velocity. Okay, so sorry, that is the velocity. So the velocity is increasing, but it's a linear graph. So if we want to find out the acceleration, then we would be looking at the slope of that line, because the acceleration is the change of velocity in a certain time. And we can see this is quite easy. So here we have, obviously the slope is 2. So that means that we have a constant acceleration of 2 meters per square second, or whatever that is. In that case, of course, we would have to change the y-axis from s to v, because then it's velocity that we look at when we have the green graph. Let's just take away that. And that is the last formula here in the script that we look at. So again, I'm writing the acceleration is the limit delta 2 towards 0 of delta v by delta t, meaning the change of velocity in a certain amount of time that is considered to be as small as possible, that's my words of the day. as small. So we see here again that it doesn't really make sense because the acceleration is not changing, and we will only be looking at movements with a constant acceleration. So this is only for you to keep in mind that the acceleration could also change. When we look at this limit thing, it's part of analysis in maths. So there we just look at the magnitude of the acceleration, but it's still a vector graphics because we can accelerate an object into different directions, and we see here that the vector properties come from velocity, the vector properties of the velocity, because that has a direction, and the acceleration is the change of velocity. And of course we then the velocity has a direction, so the change of it must also have a direction, and that's why the acceleration is also a vector quantity.